Okay, so it's my pleasure to welcome you all to the fourth Dialogue webinar brought to you from Dialogue Studios in Bramley, UK. This time pioneering Jason's new virtual reality technology where the presenters will all appear to float inside their PowerPoint presentations, APL sessions, etc. We call this webinar the Summer Intern Show, and I'm really pleased that Dialogue has managed to attract and host no less than 3 interns this summer. In the US, Becca and Stephanie have spent about 3 months learning APL in our office in Rochester, New York. Becca graduated from Robert Wesleyan College in Rochester, New York this past May with a Bachelor of Arts in Psychology, minoring in Computer Science, having started in psychology but found computers to be more interesting than most people. At least that's what my notes say. Stephanie Buettner has nearly graduated also from Robert Wesleyan with her Bachelor of Science in Computer Science. Her internship with Dialogue will fulfill her final degree requirement. Seated in front of us, Marinus is a master's student in computing science, apparently they call it, at Utrecht University in the Netherlands. Marinus has been with us here in Bramley for 6 weeks, being the second winner of the Dialogue problem solving contest to also spend some time with us in Bramley. So I'm really pleased because for one thing it's very good for us at Dialogue to receive input from people who are just learning APL and have learned a lot of other things in computer science that are new to us. Secondly, I'm really pleased that the interns have done by far the bulk of the work for this webinar, and especially I've avoided the high blood pressure involved in getting robots to do what I want. So, without further ado, we'll leave the stage first to Marinus, who's going to talk about what he's been doing, and the girls will be back a little bit later.
All right, so what I've been working on is Python, a bridge between Dialogue APL, or well, we're supposed to call it an interface now. There was some back and forth over that between some of the people here. We're supposed to call it an interface now. So I've been working on an interface between APL and Python, which everyone here has been calling Py'n'APL. So first of all, why would you want to do this? For those who might be watching who don't know Python very well, Python is an easy-to-use, highly popular scripting language, which actually has a few things in common with APL, namely that it's a very dynamic language. So it's dynamically typed. You can use it interactively in a session. It allows a lot of introspection, which has helped me in making this. And it's popular in the sciences for things like data analysis, but it's also very popular in a lot of hobbyist scenes. It's available on nearly all modern platforms, on Linux, on Windows, on Android, it's available on the Pi as well. And there are a lot of libraries available for Python. Basically, if you can think of it, then there is a Python library for it, whether it's making platform-independent GUIs, whether it's parsing, whether it's anti-gravity. And since Python is embeddable, it's also used to drive other programs for which you could use APL if you had a bridge interface. Sorry. So what I've been working on is this interface, which will allow you to access Python from APL, and the other way around too. You can access APL code from Python. It can exchange data between the two environments. It will convert it as necessary. I'll show you later in the demo. And it's possible to call functions in the other environment. So if you have APL code, you can call Python functions, which can call back into APL if necessary. And in that way, you can interface with Python you can interface with Python code, Python libraries. So let me just show you what it can do. I hope you can see this. I forgot something again. Yes. First I'm going to do this. What this does is it makes this Py object, and in the background it starts a Python interpreter to which it's now connected, which means I can run Python code now. So you can even add numbers together. But now that you can see it's working, it can fill in arguments. What it can't do, of course, is that's one thing APL can do and Python not, is add numbers and lists together. But that's what we have APL for. We can, of course, transfer lists or vectors. If I transfer some complicated, I need to enclose it. Transfer some complicated vector over a nested vector, it will just work. So if I tell Python I want the second element of this, I will get the second element of it. Because it does, Python starts at 0 like most languages. Python does not by itself support higher order arrays. So if you try that, it will split it. But one of the great strengths of Python is, of course, that it has libraries for just about everything. So one very popular one is the Numpy library, which adds exactly this to Python. So if you use that, then you indeed get the matrix back. And just to show that this is actually Python code running, I can ask for the length of this thing, and it works. We can even transfer namespaces across. So if I make a namespace and I put something in it, Python has this concept called Dictionaries, which is, it's a mapping between values and a mapping between strings and values. So that's exactly the kind of thing you want to use for this. So I can ask this for full, and it will say 42. This, by the way, APL doesn't know about this. It's all done on the Python side. These kind of ragged arrays are standard for the standard way in normal Python to transfer higher order arrays. So that was done with a reason. And of course Python can call back into APL. So if I write a little callback function, then in Python I have the APL object from which I can retrieve that callback function, and then I can call it with, for example, the argument +5. Of course, this is all the low-level stuff. What you really want to do is use, as an APL programmer, is use all those Python libraries in APL, preferably while writing as little Python as possible. So let's load in the nltk library, for example. This is the natural language toolkit. So I can, this library, for example, has a Python class in it. Which is called the WordNet Lematizer. Which I can instantiate, and which I now have, of which I now have a representation in the APL side. So that class has a function, lematize, which given, for example, yeah, they're all by the way, all the functions are shy, because in Python code there's no such thing as not returning anything, and in APL code there's really no such thing as not outputting anything if you have something to return. So if you're going to write a lot of code, then it's handy, but if you're going to demonstrate and forget to put a plus, it looks like it doesn't do anything. But so if I give it ducks, it gives me the singular form duck, but if I give it the word corpora, it gives me the singular form corpus, and if I give it the word cacti, it gives me the word cactus. So this is not just the -1 take of something, or the -1 drop of something. It's actually doing something that you wouldn't want to necessarily replicate if you don't have to. Of course, now that we have natural language processing, we might want to get some text in here as well. So let's see, have I loaded the demo in? Yes, I have. So now that I have this, I can instantiate the API. So I can say tweets, gets, say, this is all live, I have no idea what's going to show up. Get user timeline. So now I have this. This comes across as an APL vector of Python objects. This is a normal vector. I can do row on it. But these are objects, so I can grab the first one and say text. It should give me some text. So now I can grab the nltk library again and say give me all the words in here. So now I've used one Python library to bring text into APL, another Python library to parse it. But I can do all of this in APL without having to necessarily write Python code. So I can ask it what kind of I can ask it to classify everything. So now I know the is a determiner, beauty is a noun, is a verb. And since this is all APL, I could say get the second element from each, and then I get the types. I can say which ones are nouns. Anyway, you can do linguistic analysis in APL now without having to write Python code. You could do this for, at least in theory, you could do this now for any Python library you have. Except given that this is all very experimental, that might be more theoretical than in practice, but still. We can also do the opposite. We can go to Python. Oh, I'm not in the right directory yet. I can say from So now I have an APL object here. This is all symmetrical. This has started in the background a dialog instance. It's found it on the path. On Windows it goes and looks in the registry. But if you don't have it installed, it will say error. APL, of course, can add lists together, and Python understands that this is a list. Now, APL doesn't, of course, have that many libraries, but you can interface with an APL system if you have one. And you could for example, use the APL primitives in Python. So I could say it's APL. So this gives you a way to access APL from Python as well. That's basically everything I wanted to demo. The code is available on GitHub. It's still very experimental, so expect it more to... I wouldn't be surprised if it works a little less well for you than it does for me in the demo. Well, it works on Linux, on the Mac, on Windows, and on the Pi. So it's a bit slow on the Pi. You need Dialog APL 16, the Unicode version. And Python, as for Python, it needs 2.7.9 or higher, or it needs 3.4 or higher. It'll probably work with 3.4 better. And I also have to say I haven't tested this on the Pi for quite a few commits before this. And if you are more interested in this, I will be at Dialog 17 and give another presentation on it. But now, the other two are up, Becca and Stephanie, who by the way, have been the first users of this and who helped me debug it. Not entirely voluntary. Can I disconnect it?
Looks like we're good to go. So thank you, Marinus, for that introduction. I'm Stephanie. I'm Becca. And we are the other two Dialog interns. So far what we've been working on, at least this past week as we've been here in the UK, we've been messing around with some Lego robotics using APL. And so what we've been working on is this little robot we've named Alfred. And what he is a robot that you can be remote controlled by using your phone. So how that works is you have your phone, and if you tilt it forward, he should accelerate forward, and if you tilt him backwards, he should go backwards, left, right, so on and so forth. So what he is he's made out of a brick Pi 3 that is sitting on top of a Raspberry Pi 3 that is sitting on top of Lego and is connected to Lego motors. And if you're unfamiliar with Lego robotics, a brick Pi 3 is a board that's created by Dexter Industries to communicate with the Raspberry Pi. And what it does is it allows the Raspberry Pi to communicate to Lego motors. So it can send messages back and forth, and you can set the speeds of motors and sensors and run Lego robotics via the brick Pi 3. So that means you can do a lot of cool stuff with robotics, and is what made us able to create our robot here. As well as this, we were also able to use Marinus's Python bridge. So what we weren't able to do through APL code, through communicating with the motors, we were able to do with the Python, or interface, I should say. So that's been interesting to work with.
Okay, so our robot Alfred is made up of many different components. So we will be controlling his movement with a phone, using a gyroscope to measure the tilt of the phone, and that will make him either go forward, backwards, or make him turn left or right. So on that phone, we'll be running a browser that connects with MiServer, which is on his Raspberry Pi. It's running that. So MiServer will listen and send readings from the gyroscope about the direction that the phone is being tilted, and that input will come to the Raspberry Pi. It'll be form as a beta and gamma will be the degrees that we're looking for. In the Raspberry Pi, it will calculate the direction in his direction, his acceleration, his speed, all from those 2 degrees that we got from the device. That information is then sent, is using our APL wrapper class that we built around Marinus's code. We'll send those calculated speeds to the brick Pi by calling the Dexter, our brick Pi Python library, which will send the input into the brick Pi, and then using SPI, that's how it will communicate with our Lego motors. So this is just a sort of a diagram of what I just talked about, just showing that the phone talks to the Raspberry Pi, which has the server on it. It then uses our APL wrapper to communicate with the Python bridge, which calls the BrickPy libraries, communicating with the BrickPy, and then resulting in movement in our Lego motors.
So now that we've had a little bit of an overview of the components that make up Alfred, we're going to talk a little bit more about the details and process of how we were able to make him work using the code. So first of all, we're going to talk about our APL wrapper class to the Python interface. But first of all, when we started looking at how we could control Lego robotics using APL, we were using the original BrickPy, and this was an older version of the BrickPy, and we were trying to use APL code to directly talk to the motors, and we were able to get APL to communicate with the motors. However, it didn't work the way we wanted it to. We were able to turn the motors on and off, but we couldn't really control how well they worked. So we eventually switched over to using the BrickPy 3, which is a newer version of the BrickPy, and it has a different interface. So once we started using that, we realized that we could use this Python interface to communicate with it, because Dexter Industries, along with the BrickPy, has made a Python class that you can use to send commands to the Lego robotics. So you can use Dexter Industries Python class in order to set the speeds. And so in our code, we pretty much just wrapped the Python bridge connecting to Dexter Industries Python class. So in our constructor here, you can see that we're creating a new object of the Python bridge and importing Dexter Industries class. And in the set motor power method, we're pretty much just calling the code that they wrote to run the motors. So we didn't have to write any of this in APL. We were simply able to call the code that they had already written. So that simplified our job a lot in getting Alfred to run.
All right, so one of the first things that we were looking into, that was our first task, was to make Alfred go forward or backwards. We just needed to provide some power to each of his motors. And so the Lego motors that we have, they can take an input of a speed between -100 to 100. So our first attempt to make him go forward is we kind of looked at it very simplistically by just saying that we would take whatever target speed that we wanted to make the motors go and use whatever sign that was to determine which direction he was accelerating, and then calculate the rate based on the angle. Now the problem that we ran into with this is that it did not cover all the cases, because Alfred would never slow down. He would always be accelerating toward the fastest speed possible, And so the only time that he would ever decelerate at all was if we reversed the direction, drastically reversed the direction of the speed that, of the direction that he was going in. So, because of that, we decided to come up with a new approach, which instead we decided to base it on the difference between his target speed and the speed he is currently going at, and using that to determine the direction that he would accelerate at. So our first step, which you can't see in this code here, is that we calculated a target speed, which is based on the angle of the tilt. Just set it so that if you tilt him forward more, he will be able to reach a higher speed, and then it varies based on how much you tilt it. But here we have our acceleration method, which all we're doing here is just we get the difference between target speed and finding the sign of that, and multiplying our results based on the sign to determine which way it's going. But to actually get the acceleration rates, we set a max speed, and we took a percentage of that, took the percentage of that speed in relation to that to create the acceleration rate. And that's about it.
So similarly to how we started out with one approach to acceleration and switched approaches halfway through as we realized it didn't work, we also did that with turning. So our original approach to turning was we would set one wheel to the current speed that the robot was going. So if it was going speed of 45 forward, and then you turn it, one wheel would be going 45, and then we would decrease the speed on the other wheel as a function of how much you've tilted it left or right to turn. So he'd be going forward, one wheel would stay the same, and if you tilt the phone, the other wheel would be decreased in speed, causing him to turn one way or the other. However, we realized this created way too sharp turns, especially at high speeds, because in this case, you could have the robot going with a speed of 100 in one wheel and 0 in the other wheel. So this would create like a really sharp turn left or right. And we thought that that was just really hard to actually maneuver him, because it was hard to keep him going straight forward without him turning, as it was a little bit too sensitive. So we adjusted our approach to turning to something different.
Right, so based on the degree of tilt, we would be setting a difference between the two wheels. So as you, just to cover it, you can see on the code here that we're setting a threshold. One of the other issues that we ran into was that it was very difficult to keep Alfred going straight, because any little tilt would make him start veering off into the opposite direction. So we set a threshold saying that if it's below 10 degrees or anything, we're just going to set that as 0. So that's what is happening here with the tilt threshold. But but we're receiving an input of gamma here, and gamma is either going to be negative or positive depending on which direction you want. If we're going left, it's going to be negative. If we're going right, we're going positive. If we're going right, it's going to be positive. And then we're going to calculate the percent of tilt in relation to our maximum degree that we're allowing the phone to tilt in order to have input. And we're taking that percentage, and then we're taking our max difference, which the maximum difference is just the maximum difference allowed between the two wheels. So if we are tilting all the way, however far we can, that's going to be the difference. But other than that, we are going to reduce it so it's in relation to the lower the tilt, the less of a difference is going to be between the wheels, and then it increases. And then the thing with how this works is, after we calculate that difference, is we need to add it to one wheel and subtract it from the other. So that's what this defund here is doing. It's just taking the direction and the difference, determining which direction it's going by, also just subtracting and adding from one of them, and then adding that to our base speed that we have. And if we wanted to go backwards, we're just reversing the two numbers there.
Okay, So here's a little bit about how we went through building and testing him. As you can see, the picture on the left is when we were first putting Alfred together. We have all of our Legos strewn all around the table. On the right is actually the first time that we tested Alfred in a live test. And this was a little bit interesting because we realized that we had the angles mixed up, or the tilts mixed up in our code. So the forward-backward tilt in our code we were treating as left-to-right tilt, and the left-to-right tilt we were treating as forward-backward tilt. So that meant that when we were tilting it forward, it was tilting right or left, and so on and so forth. So that caused him to behave a little erratically. And in this case here, he got himself wedged under a cupboard by trying to climb the wall. And it took a little bit to get him out because we could not accurately control him. So now we have something working slightly better, which we can show, hopefully, in a little demo here.
Hopefully. I think we're running.
Oh, here we go. I don't know if you can see my phone here. I'm tilting it forward. He's going forward. So I tilt it to the right. He turns. He also goes backwards. You can spin him in place. You hold the phone flat to stop it. Sometimes he likes to run up tables. Oh, there he goes.
I think he's game over for tonight.
Okay, well that's a little bit of Alfred in action. As you can see, we don't have much space on the table here, so we decided not to try to actually show him herding ducks live, but we did get a video of him running ducks around a table, or on the floor.
Is it running?
Here we go. Here's a less violent video.
It's pretty bad.
And that is all we have for you today.
Okay, well, thank you. That was a lot of fun, especially when he went off the edge. I'll
Live
kneel down
demos.
here. So, that was the Dialogue Summer Intern Show. The next transmission will hopefully be from Dialogue 17 in Denmark in about 3 weeks. Is that it, Jason? I think. We don't know for sure until we get there whether we'll have the bandwidth and so on to do the transmission. If that fails, the next show will be in October. That's all from us here in Bramley. Thank you very much. See you next time.